the basics of friction. And we'll start by talking about how we deal with static friction. Again, static friction is on a scale. It can go from 0 to some maximum value. I don't know how far we got yesterday, but how you write something like that can go from 0 to a maximum. Did we talk about it? So it's an inequality. And I talked about mu and all that too. Excellent. So this is how you express a force that goes from some minimum value or 0 up to some maximum. Now, I want to be as clear about this as I can. Because this is an inequality, it can be any value between 0 and this maximum. So if I tell you that an object is experiencing static friction, I'm not telling you how much friction it's experiencing, because it can be anywhere in that range. Using this equation is hard because you can't just solve this. I can't just plug in these to figure out how much friction there is, because it's any value up to the maximum. There are some things that you can look for in a problem that will help you decide how you use this. For example, if you're asked what the maximum force is, what max friction or max angle, the word max suggests you're approaching the limit here. So if I ask you, I'm going to tip the book, what's the maximum angle I can tip the book before it slides? That's approaching the transition. When I ask about the max, I'm talking about transitioning this from an inequality to an equality, because we're getting to the max condition. This is a hard idea, but let's talk about it in practice, okay? So make that small, put it over to the side, and put it in practice. There's your first job, you're working at Publix, and your boss tells you there's a box in the middle of the aisle. I need you to go over and push it across the aisle. Okay? So you're going to push the box. Let's say the box is 50 kilograms, big and heavy. And let's say that the box itself is on the ground and there's a coefficient of static friction of 0.4 between the box and the ground. So listen to how I'm going to say the question. How much force do you have to apply to get the box to start sliding? Do you hear how I'm asking this question? Because it's possible you could push on the box and it won't go anywhere because you haven't pushed hard enough to exceed friction. So you'll push harder and it still doesn't go anywhere. And you'll push harder and finally you'll reach a maximum threshold. So when I say the question, how much force do you have to apply before the box starts moving, I'm asking for you to approach the threshold. Does that make sense? But I want to teach you how to use an inequality. I have fear that you don't know how to use it. So first things first, could you draw me a free body diagram to describe the forces acting on the box? I'll put a little dot here, and in a moment I'm going to call on a couple of people until I think we've gotten all the forces. Now that we have all of our forces, we'll do horizontal, the x direction. I'm going to make this the positive direction and this the positive direction. Is that okay with you guys? And again, the system's in equilibrium because we're dealing with static friction. So net force in the x direction equals 0. And I see two forces in the x direction. I see the applied force and the frictional force, and they have to sum to be equal to 0. And then similarly, in the y direction, net force equals 0. And I see two forces in that direction too, do you? So normal force minus weight equals 0. All right, we've used Newton's laws. They've given us a set of equations. Now we want to see if they can be used to tell us something about the problem. We're interested in figuring out how much force to apply. Again, I want to remind you, getting here, this part is hard for us. We've demonstrated we're struggling with it. But this is where the actual problem begins. This is where the analysis comes in. Now, we have some things we can do for substitution, right? For example, you're aware that we can substitute in for the weight. What would we substitute in for the weight? Yeah, so I'll substitute mg in for the weight. Now, I'm just going to slide all this to the side because I don't really care about the picture anymore. And that's going to tell me right away that normal equals mg. But I think that's the only substitution I can do. I know I can say the applied force equals the frictional force, but I don't know that you're aware of how to do substitution with an inequality. Have you guys done substitutions with an inequality before? So I'm going to tell you how I would like you to do it, because I'm not sure you've done it before, and if you have, I don't know what you've been taught. But when we have an inequality, I think the best way for you to work with an inequality is to substitute into the inequality. Meaning, I'm not going to take this and put it here. I'm not going to do that. Because I don't really know that the frictional force equals that. For substitution to work, it has to equal something. And this says that the frictional force is less than that. So instead, I'm going to substitute into my inequality. Where I see the frictional force, I'm going to put the applied force, because I want the applied force. So I'll do that substitution first, and I get the applied force is less than or equal to mu times the normal force. Well, that's a step in the right direction, because my problem gave me mu as 0.4, but my problem didn't give me the normal force. So I think I'm going to have to do a substitution again. Right? I'm trying to analyze the problem. Do you see another substitution we can do? Excellent. So that substitution, replace the normal force with mg. How's that look? So this tells me now that my applied force has to be less than or equal to mu s mg. Now, we have something to put in here, right? Each one of those things we have. In fact, if I looked at the numbers that we were given at the beginning, my applied force is going to be less than or equal to 0.4 times 50 times 10. Does that make sense? I believe this is 125. You could check, though. It's probably a good idea if you do. It's 200? Oh, I was dividing by 4, not multiplying by 0.4. Thank you. I knew you should check. Now, hear me out. The question said, how much force do I have to apply in order to get the box to slide? Remember the question? Now, what we did is we said the net force equals 0. This says that if I want the forces to remain balanced, I need my force to stay less than or equal to 200. So if I push on the box with 200 newtons or less, the box doesn't move. That's what it says. So how would I answer the question? I would probably just, go ahead.
The applied force, you need to apply more than 200 newtons.
That's how you'd answer the question. That's right. This is how this problem is done. The static frictional force will tell you how big the frictional force can be. So it'll tell you what you have to work with. But if you want to exceed that, then you would break the static frictional force, and then you would be able to slide the box. This says I had to push with more than 200 newtons of force to get the box to slide. Once static friction breaks, what kind of friction takes over? Kinetic. So generally, kinetic friction is less than the maximum frictional force. Generally, that's what you get. So I'm going to ask you to do another problem now that's based on this one. You apply 201 newtons of force. Right, that's enough to break the static friction, correct? When you do, the box begins to slide, but the kinetic friction coefficient is only 0.2. What's the acceleration of the box? Does everybody understand the question I'm asking? We've exceeded how much friction we have, so we know the box is going to start to slide. But immediately, static friction goes away and kinetic friction takes over. So I'm asking for you to tell me, what will the acceleration of the box be? Because what's happened here is suddenly this force, this frictional force, has gotten much smaller. And it's no longer static friction. It's kinetic friction. We have several minutes. Try and see if you can come up with the acceleration. Equals ma. This is a second law problem. Provide a little extra guidance. We're now dealing with kinetic friction. Do you guys remember what the equation for kinetic friction looks like? It looks a lot like the other one, doesn't it? Except that for kinetic friction, it's equal to mu times the normal force. So we can do substitution with that one, right? It's not an inequality. However, let's look at what I have. I have, in the x direction, can we do Fa minus friction equals, is that going to be ma or 0? Ma. I'm pretty sure the box is going to be accelerating to the right, not up or down. So ma. And in the vertical direction, what do we have? It's going to be equal to 0. There's still two forces there too, right? Normal minus weight equals 0. All good? All right, we want the acceleration. I think we've got a lot to do. This is where the Newton's law gets us here. But now we've got these three things we have to somehow mash up together. When I look at the numbers, I have this number. I have this number. And from the previous problem, I'm pretty sure I'm going to get this number too, right? So I have some things, but we got to do some work to get it all together. For example, I could start by saying, well, normal minus mg equals 0. I can substitute, right? Whenever we see weight, we can put mg in there, which means normal equals mg. Does that seem like okay? All right, we got to start. That's a good place to start. In fact, I'm pretty sure I could use this to say that the kinetic friction is equal to mu k times mg. Could I do that too? I know all of those things. I mean, mu k is 0.2, and m is 50, and g is 10. Right? I know all of those things. So mash them all together, and I'll get that it's 100 newtons. How's that look? Remember, this is the analysis. We're trying to, what do we have, and can we use the stuff we have to figure some things out? Now, in this problem, we were also given the applied force. That's 201. And now I just figured out the frictional force. That's 100. That's going to equal ma. Well, look at that. That's what we wanted. How fast does the box accelerate? That's right there. Do a little math magic and find out A equals 2 meters per second squared. I didn't say these are easy, but I do think that these are problems that you might be capable of doing. But it takes a lot. Wouldn't you agree? Try another one. Same level of difficulty or harder? Same. How about I'll make it about the same? I don't know if you want to go. I'll keep this in the same vein as the problem we just did. Was it clear to you that we had exceeded the amount of friction there without trouble? So let's do a similar problem. Let's have a box on the ground. Let's say there's a coefficient of kinetic friction of 0.2. Let's say the box is 50, but this time the employee pulls the box. With a force of 200 newtons, but an angle of 30 degrees. So they're pulling on the box. What would be the acceleration in this circumstance? This is a little bit different. We've done a problem like this before though, right? This is not much different than stuff we've already done. And I think a good start is to ask, is this going to be a first law problem or a second law problem? Heck yeah, it is. And can you draw a dot and put some arrows on it? It's a good place to start. So we have only 5 minutes. So these problems can be kind of long if you haven't noticed. So let's start looking at all the arrows. Did you put a downwards arrow? Good idea. I'm going to put a downwards arrow too. And what should I call that downwards arrow? Weight. And look, you don't have to, no circumstance here. Weight is mg. The mass is 50, so this is 500. You know what I mean? We can do a few of these steps, out of order if you'd like. And we're pulling on the box, so I can definitely put that one in there, right? So I'm going to draw another arrow, and I'm going to make that arrow like that. It's 200. And it's at an angle of 30 degrees. Is there another arrow I should draw? What other arrow should I draw? The normal force. That's a good one. Now, I'm going to be careful to draw this one a little smaller. I'm pulling up on the box, right? The normal force is a responding force. So if I'm pulling up, the floor doesn't have to push up as much as before. You follow me? This is important, and I want you to see this. By pulling up on the box, I reduce the normal force. If I reduce the normal force, what other force do I reduce? Friction, sure. This is how you reduce friction. Our football team could learn. That a good one to use? What would I call this one? What's that? Friction. There we go. This is kinetic friction. All righty. Okay. Unfortunately, we have a force that is off axis, right? So if I consider my axes, I think I'm going to have to take this force and break it up into a sideways force and an up and down force. Do you guys see that too? So my sideways force, 200 cosine 30, because it's the adjacent side. And my up and down force, 200 sine 30. You guys see that okay? All righty. Yay. Almost done with that stuff. So I think now we can over here write net force in the x direction and net force in the y direction. You guys said that this was a MA problem, so which one of those gets the MA? The x, that's right. We're going to make the sideways the direction of the acceleration. And that means up and down is 0. So I'm thinking the sideways force is first. Is that okay? So I see 200 cosine 30 minus the frictional force equals MA. Do you guys see that all right? I do. I'm pretty happy with that. Let's do the up and down ones. There's not 2 of them, right? There's 3 of them. I've got the normal force, sure. What else is pointed upwards? Yeah, so plus 200 sine 30. And then I have something put downwards, right? 500 equals 0. All right, let's see. I think we can find the normal force, don't you? And I'll remind us that we have another thing that we can bring here. We have kinetic friction is equal to mu times the normal force. If I can figure out the normal force, I can figure out the frictional force. So let's go with it. Is the normal force going to be, let's see, 500 minus 100? So 400 newtons. All right, well that means my frictional force is going to be 0.2 times 400. So I made the frictional force a lot smaller, didn't I? So is that 80? So now I know it's lots of substitution. Are you seeing all this substitution? It's a lot of it. And now I have 200 cosine 30. Oh my word, this is taking forever. Equals 50 times A. You think this is doable? It's a lot of steps, isn't it? All right. Folks, practice this weekend, please.